Everybody. So this next unit is on moments and centers of mass. Sometimes I cover this section, sometimes I don't. But the idea in this case is that we've got. Sorry, let me maybe adjust the camera here a little bit. So we've got. We're going to sort of develop our mathematical model in stages here. And the idea basically here is that we're trying to find centers of mass. So if you have something balancing on a, say, a seesaw or teeter-totter, for example, right, where we want to try to place things in such a way or on a balance so that they balance out, right? So we can talk about let's talk about the one-dimensional case here first. So this will be the first stage. So in this case, we've got masses M1, M2, and M3, and those are distance of x1, x2, and x3 respectively from the fulcrum of this thing, right? So this is like a seesaw. It's allowed to sort of tip back and forth along the fulcrum there. And the resulting system might balance or it might not, right, depending on how large the masses are. And you might remember that when you're dealing with levers, right, the torque or the amount of rotation, right, or strength of force depends on how massive the object is and also how far it is from the fulcrum. So maybe you have like a really heavy mass here, and then you have maybe a lighter mass here, and maybe a lighter mass here to kind of balance everything out. But and I guess this isn't particularly important, but one thing you might be aware of is when you throw something or slide something, at least not under the influence of gravity, for example, it will revolve or rotate around its center of mass. So for example, if you take like a wrench like this and slide it across some ice, right, so the gravity isn't affecting it, it's not going up or down, it will rotate around its center of mass, right? So for example, if you ever see any science fiction movies where they have an asteroid moving around and it's not moving around its center of mass, right, that's not really depicting physically what really happens there. So this isn't really that important, but just one thing to keep in mind. And so we usually want to know where to place the fulcrum, right, to make the system balance. That is, at what point we'll call the fulcrum X bar to place it to make the torques equal to 0 or to make the teeter-totter balance, right? And the torque of a mass about the fulcrum is basically where you take the sum of you take the distances from the fulcrum to each mass and then multiply it times the force at that point, and then you could sort of add them all together, right? So you could just take the distance of the kth particle minus the fulcrum times the mass of the object times the force of gravity. Now if you move to the 2x2 case, then if you have an object sitting on a plane, then its torque will basically, or its moment, you'll have a different moment around each axis, where you might have a different moment in the x direction and a different moment in the y direction. So imagine you have this object, imagine you've got sort of a flat plate here, right, and it's balanced maybe at this point here, right, the fulcrum is here, and you're trying to balance this out. The torque or the force in this case would be this length times that mass, and that length times that mass, or the force of gravity, right, rather than the mass. And so in order for this to balance out, right, you'd maybe have to have a corresponding particle over in this region to balance that out, right? Or maybe you'd have to move the fulcrum to the middle and have another particle there. So let's say, for example, we have a fulcrum here, and we've got a bunch of masses, and imagine these are placed on a flat plate, right? Imagine that you've maybe got a plate shaped like this, and it doesn't weigh very much, right? You can neglect the weight of the plate. And the question is, where do you place the masses on the plate to get the thing to kind of balance on the fulcrum there? So what you have to basically do is add up all the contributions of the y moment, make sure those are 0, and then add up the contributions of all the x moments and make sure those are 0. Now, you can extend this to a continuous object, so instead of a bunch of discrete objects like this, imagine that we've got something like this where the object is made up of a bunch of little tiny particles, right? And the idea basically is you'd have to figure out what the moment is for each particle and add those all together, right? But you sort of got infinitely many particles here, so that's sort of impractical. So what we'll do is we'll take the moment of each strip here, and then we'll integrate and add the moments of each strip together. We'll call the center of mass x tilde, y tilde, this little squiggle is tilde here. Some people just call it x squiggle and y squiggle or something like that. But so the center of mass in the x direction is the moment in the y direction divided by the mass of the plate, and that's given by the sum of the sorry, I guess this is the center of mass of the strip, right? The sum of the center of masses in the x direction of the slip times the change in mass of the strip over the mass of the strip, right? So this will be like the mass of one of the y strips, and then the mass, or the x strips, and the mass in the y direction, right, would be the center of mass of the strip in the y direction times the change in mass over the mass of the strip. And so what you'd want to do then is add these all together. Right now, the continuous version of this, again, is you'd want to basically integrate. Right? So the moment about the x-axis in this case will be given by this. So this is basically just the top of this equation. Right? And the moment about the y-axis will be given by that, and then that'll be over the mass of the entire plate. So again, the center of mass in the x direction is m sub y, and the center of mass in the x direction is m sub x, right? Basically just these two things that I had in the previous slide. So let's look at a particular example. So let's say you have a triangular plate shown on the next slide, has a constant density of 3 grams per square centimeter, and we're sort of ignoring the thickness of the plate. So we want to find the plate's moment m sub y, right? So this should be a subscript here, m sub y, about the y-axis. The plate has a mass of m, and then the x-coordinates of the plate's center of mass. And some of this you can kind of do by a little bit of intuition here, right? So this has a uniform density here, right? The density of this thing doesn't change depending on where you are, right? It's 3 grams per square centimeter. And so we want to find, we basically want to find the point x bar, y bar, so that you could sort of balance this thing on the tip of your finger, right? So imagine that you were trying to balance this on the tip of a pencil. Where would you want to put it? And in a way, if you think about it, that since the mass is uniform, that doesn't really matter all that much. But you can kind of eyeball this, right? I mean, if you think of it, more of the mass is down here than up here, and more, so I don't know exactly where it's going to be. I'm just sort of guessing, but sort of somewhere down there, right? Because that's where most of the mass is when you balance it. Now keep in mind this is further away, so again I'm just sort of guessing, but if we do the calculations you'll get a more exact answer, right? And imagine you're designing this for some sort of mechanical system, right? You don't want to guess, you want the exact value, or as exact as you can make it. So again, we can either have the strips going in this direction, or we can have them going in this direction. You should get the same answer. But the idea then is we want to take the mass of the strip and then multiply it times its distance from the y-axis, right? And you might say, well, that's not really the fulcrum. Well, the idea is if this, we know in advance that this thing is going to balance, we can kind of make the fulcrum whatever we want. So the height of the strip is given by 2x, right? And the thickness of the strip here is given by dx. And so what we want to do in this case, if you want to look at the moment in the y direction, right, if we want to calculate m sub y first, and then the mass of the plate, and then divide them, right, to get the x-coordinate of the plate center of mass. We're not going to worry about calculating the y center of mass in this particular case. So we'll do, so we need x tilde times dx, right? Remember, that's the formula for that, right? And remember, this is the center of mass in the x direction of the plate. So in this particular case, just clarifying this a little bit more here, right? This distance will be x, and then the mass of the plate, the mass of the strip will be 2x, and its width will be dx, right? So I'm basically taking x times 2x dx, and that will give me the distance that the plate is. Something doesn't seem right here. Maybe I'll have to come back and take a look at this sliding in. But so you basically take the again the mass, right, which is given by that times its distance, right? So the mass would be given by that. Oh, that's right. We have to multiply times the density, which is 3, right? And we have to multiply times the density, which is 3 there, right? So you'll get basically, the rectangle is given by 2x times dx, right? That's the height and the width, and then you multiply by the distance x from our axis of rotation, which we're assuming to be the y-axis in this case, and then multiply it times the density, which is 3, right? Then integrate that, and you'll get 2 for that. And then the mass of the plate, you don't have to use calculus for this. It's just a triangle, right? So you could just take 1 times 2 times the density, which is 3, right? So the mass of the plate is going to be, what, 6, I guess, right? I guess it'd be 1 times 2 times a half, which would be 1 times the density, which would be 3, right? So that's 3. Or you can use calculus and then take this divided by that. Okay. And so you can kind of see it's where I was estimating. Right? I sort of, maybe that's not perfectly correct, but if this distance is 1, right, the x coordinate, it should be closer to 1 than to 0, right? Okay, so there's one example. Now, again, you could do this using horizontal strips also if you want. So in this case, we could make the strips go this way. So if you do that, again, we want to calculate the same thing. Now, in this case, the equation would be given by this. Right, so we're still calculating x bar, so we need m sub y and m. And so in this case, if you look at the equation, where is this strip? Right, so since we're integrating with respect to y, the mass of this strip then will be given by the length of the strip here, right, which is 1 minus y over 2. So that'll be 1 minus y over 2 times its thickness, which is dy, right? And then the question is, where is the center of mass of this strip in relation to x? Well, the distance here will be 1 plus y over 2 divided by 2, right? So it's basically the average of this distance and this distance, right? So this distance is always 1, and I'm adding y plus 2 to it, which is that, and then I'm taking the average, right? So the distance there would be 1 plus y over 2 squared. And then, again, I also have to multiply it times the density, right, which is 3 also. Right? And that 3 could just come out front. Again, since it's uniform density, that doesn't really matter anyway. But then if you simplify that, right, that should give you that expression. Maybe just to clarify that. Right, so I'd add these two together. So I'd have 3. This would be 2 plus y squared all over 2, but then that's divided by that other 2, and then you get 1 minus y. Let's just combine these together. 1 y minus 2 minus y over 2 dy. And so then I'll get 3 times 2 plus y times 2 minus y. This will be all over 4, right, because I've got 2 divided by 2, and then I've got a 2 on the bottom. So I'll just get 2 times 4, which is 8. I'll get the 3 on top, and then 2 minus y times 2 plus y, right? That'll give me 4 minus y squared, right? So that's the integral I'm doing there. There's some algebra to simplify that there. And then just go ahead and do the integral, and you get 2 for the top. And again, the plate, the mass of the plate is the same. And if you think about it, this should be the same as the answer that we got before, right? Because the center of mass isn't going to change. So the center of mass is just 2/3. So let's look at another example here. Let's say that you want to find the center of mass of a thin plate covering the region bounded by this parabola and below the x-axis. Assume the density of the plate is given by the following. Right? Now, again, in some cases, you may be able to just guess this. In this case, we want to find the x and y center of mass. And again, the reason why we say thin plate is we're assuming the plate has no thickness, right? Which is a little bit unrealistic, but if it's a thin enough plate, right, we don't necessarily want the thickness to come into play. And now in this case, the density varies, right? So if you take a look at what this thing looks like, right, it looks kind of like this. Right, in this case, the density is given by 2x squared, so that means that the density here in the middle is really thin, right? Or, well, either the plate's really thin here in the middle, or, you know, it's made of a different thing, but most of the weight is distributed on the side. So maybe if you looked at this, if you kind of took it and turned the thing this way, right, it would maybe look like this from the side, right, where I've used the thickness sort of in place of density. So maybe maybe the object is made of a light material here, then a more dense material as you go out to the edges. But the idea is it gets more dense out here, and you want to find the center of mass. Now, in this case, you know, you can kind of guess the center of mass. In this case, you know, if I had to sort of estimate, the object is symmetric this way, right? So the density is given by 2x squared. So the object's center of mass in the x direction would be 0, so it should be sort of centered on there, and then it's denser up here, right, than it is at the bottom. The further away you get from the x-axis, the y-axis, the more dense it gets. So I'm guessing that the center of mass would be somewhere closer to the bottom than to the top, but it should be on this axis, right? We may not calculate the center mass for the x direction because we can kind of just guess that, but if you do calculate it, it will give you the right value. So let's at least calculate the center of mass in the y direction. So just to remind you of that, right, the center of mass in the y direction will be given by this, right? So we'll need to calculate this, or sorry, the center of mass in the y direction is given by this. We'll need to calculate m sub x, which is that, divided by the mass of the thing. Now the mass of the thing in this case will be harder to calculate because the density isn't uniform here. Right, so in this case, let's use vertical strips in this case. So the question is, what is the mass of an individual strip here, right? Well, the mass of the individual strip is the thickness, which is dx. And let's assume we're doing it this way. You could maybe integrate this way as well. But let's just go one direction in this case. I just did that last example to show you that you should get the same answer whether you integrate in the x direction or the y direction. But so the center of mass of the strip, right, should be given by x, and then the height of the strip here will be given by the height here divided by 2, right? This point here is always in the center of the strip, wherever that is, which is the difference in height between the curve and the x-axis here. And since we're talking about the calculating n sub y, right, we want to look at this distance here, which is given by y over 2. And then the delta here just stands for the density. So what we've got basically is we've got this thing squared, right, so if you look at the formulas here, you can find them back here, right? So we're looking for this, right? So we've got this formula, again, divided by the mass. So again, the mass of the strip here is just going to be dx times 4, times the height of the strip, right? Which is given by 4 minus x squared. So that's the area of this rectangle. And then you're having to multiply it times the center of mass of the strip, right, which in this case is 4 minus x squared over 2. And then you're multiplying it times the density, which in this case varies, right? Remember the density in this case, I think, was 2x squared, right? So those 2's will cancel. And you'll get 4 minus x squared times another 4 minus x squared, which gives you that. Again, delta was just what I was putting in for the density, so if you replace that with x squared, you'll get that. And then just work out that integral, right? So you'll get that. Now that's the top of this, right? So now we need to calculate the bottom, which is the mass. Now in this case, we can't just calculate the area and multiply it times the density, because the density varies here, right? So again, we don't have to worry about the moment arm in this case, right? We're just calculating the mass of the strip, which is going to be 4 minus x squared dx, and then multiply that times the density. Then what you want to do is just integrate that. That'll give you the mass of the strip, and then just take this number divided by that number. That gives you 8/7. So again, if you think about it, you know, the distance from here to here is 4. 8/7 would be, you know, 1 would be right about here, so a little bit more than 1, right? So it's a little bit further to the bottom than what I was indicating. Right? So there's another example, and again, we won't bother calculating the moment of the moment in the y direction because we know it's, or in the x direction because we know it's going to be 0. if you did calculate it out, you would get the same thing. We might do that for some other directions. So let's look at modeling the plate bounded by two curves with vertical strips. So let's say maybe the curve isn't, up against the x-axis. Let's say that your plate is between two curves and you want to calculate the center of mass there. So again, let's say you want to find the center of mass of a thin plate of constant density, delta, covering the region enclosed by the curves. So in this case, all you have to do is just add the mass of the two curves and take the average. Right? So let's say you've got two curves here, and again, you could kind of build this up geometrically if you want to. You could just kind of plug into the formula. Again, I always kind of like to know what's going on here. So if you think about the strip here, right, we're integrating this way. So the thickness of the strip here will be dx, and the height of the strip will basically be, if you think about it in this case, right, it'll be, this length minus that length. So the length or height of the strip will be this distance, which is given by y is equal to x squared minus 3 minus the distance negative 2x squared. And then here, what you want to do is multiply by the center of mass of the strip, right? Now the center of mass of the strip in this case will be the average of the two heights, right? It will basically be what I was calculating here, right? If I take this distance plus that distance and divide by 2, I'll get that. So if I take the x squared minus 3x plus the negative 2x squared and divide that by 2, right, that'll give you the distance there. And then we're trying to find the moment in the y direction here, right? We could do it in the x direction, but in the x direction, right, I mean, assuming that the density is constant, which it does say that, right? If you think about it, the center of mass in the x direction should be 0, right? It should be laying somewhere on the y-axis. So if you look at, where is the distance of this point, what's this length, right, that would be the thing we just calculated. Right? So go ahead and set up your integral there. Right, and I guess we'll have to know where we're integrating from as well. So if you set the two curves equal to each other and solve, right, you'll get that they'll cross at 1 and negative 1. So again, the center of mass of the strip, again, is given by this average distance, which is the distance from here to here, plus the distance from here to here divided by 2. Right, so if you simplify that this expression which I just had here, right, you'll get that. And then the length of the strip, like I said, is it's this distance from here to here minus that distance, right, which would be given by that. And so the area of the strip then is going to be the length of the strip, which is given by this, times dx, right? And then we have to multiply it times the length of the lever arm. And then we don't know what the density is, so let's just call it delta for density. So the mass then, again, is given by the area, which is given by this, times delta. And the moment of the strip, again, is given by that. So take your area function times this, right? Bring that 2 out in front, and then just integrate that function from negative 1 to 1. Now keep in mind our answer will have a delta in it because we don't know what the density is. All we know is the density is some constant value, so we could replace delta with some constant value there. So that'll give you the mx. And then the mass of the strip, again, we'll just ignore the moment arm part, right? It'll just be that integral, and then just divide, right? And then the densities will divide out anyway. And then again, that'll give you the moment in the y direction. Again, we could calculate the moment in the x direction, right? But it's pretty clear that that's 0. Okay. Here's another example. Let's say we want to find the center of mass for a thin plate bounded by the curves given on the next slide between 0 and 1. And let's say that the density in this case is x squared. Okay, so here's our two curves, right? The curve in this case is, one curve is the square root of x, another curve is x over 2. And the thing is that the object gets more dense as we go further in the x direction, right? So like when x is 0, the density is 1, or 0, right? When we go to 1, the density will be 1 squared, or 1. So the density goes from 0 on this end to 1. So I don't know if the thickness is changing necessarily or not. We're assuming that it's not. But the object is heavier on this end than it is on this end, right? So again, if you think about, where's the center of mass, and, keep in mind the center of your mass should be somewhere inside the object. If you do a calculation and the center of mass of the object is like out here or something, that would be impossible, right? Imagine you're trying to balance this on your finger. Here, I can't lift it. Imagine you're trying to balance this on your finger, right? Imagine it's not floppy like that, but it's a straight, rigid thing, right? Where would you put it? Right? Your center of mass should be somewhere inside the object, not on the outside. So in this case, again, let's calculate both moments. So we need the mass for both moments. So let's calculate the mass of the object. And in this case, we'll go in the x direction. So we're calculating the mass of an individual strip. So the thickness will be dx, and then the length, or the height of the strip, will be given by this curve minus that curve. So we'll take the square root of x minus x over 2, and then we'll multiply it times the density, which is x squared, right? So this is the density. So go ahead and work this all out, right? And you'll get 9 over 56 for the mass, right? Remember, that'll be the same in both calculations. So remember, regardless of whether we're calculating the center of mass in the x direction or the y direction, right, we're calculating the same thing on the bottom, right? So we just calculated the mass of the object. Okay, so we've got that. Then for x bar, we need to calculate this. For y bar, we need to calculate that. So again, this is just the mass that we just calculated. I just inverted that because we're dividing by it. So the moment in this case will be the integral of x tilde dm, right? So we basically need our mass computation that we had up here, but then we need to multiply it times the length of the lever arm in the direction we're looking for. Okay. In this case, if I can't find the drawing I was looking at here, right? But so remember, you've got the square root of x and x over 2, right? Think about what the moment would be in the x direction, right? You've got this strip. Think about what is this distance going to be, right? The distance of the strip is just going to be x. So I'm just taking what I had before, the mass, and multiply it times x. Go ahead and work that out, right? Again, I'm dividing by 9 over 56, which is the same thing as 56 over 9, and I get that for the center of mass in the x direction, right? Which, if you think about it, that seems about right. I mean, it should certainly be less than 1, right? This distance is 1, so I'm saying that the center of mass is somewhere right around there, right? At least in the x direction. Now, in the y direction, I need to take the moment in the x direction, so the question is, where is the center of this strip in this direction? Well, in that case, I need to take the average of these two distances, right? So the distance from here to here is the square root of x. The distance from here to here is x over 2, and then I need to divide that by 2. So what I would want to do then is take my moment in that direction and multiply by that, right? So maybe I just kind of plugged in here, maybe to show you where this is coming from, right? So this is just the density again, and for this again, I'm going to have the mass of the strip, which is given by the square root of x minus x over 2 times dx, right? That's the mass of the strip. And then I need to calculate its distance from this. Think of this as your axis of rotation, right? What's the distance here? Well, the distance here is going to be what I just calculated, right? I want to take that times the square root of x plus x over 2 and divide it by 2 and multiply those together, right? So if I multiply those together, let's maybe simplify this first. Right, if I add this together, I'll get 2 square root of x minus x all over 2. And then for this, if I add these together, I'll get 2 square root of x plus x all divided by 2. But that's also all divided by 2, so that'll be divided by 4. So if I multiply those together, right, I should get this expression, right, and then just multiply by that, right, because I'll get 2 square root of x times 2 square root of x, which will give me 4x. The middle terms will cancel, right, and then I'll get minus x times x, which is minus x squared. And then on the bottom, I'll get 2 times 4, which is 8, right, and then I can pull out a factor of 2 here out of the bottom, and then that should give me that expression, right? So right, because I'll get 2 times 4, which is 8 on the bottom, and then just 2 on the bottom because the 4 and the 8 are going to cancel, leaving you with a 2 on the bottom, right? So so again, that's kind of how you build that expression, work it out, right? And then we already calculated the mass, so I guess I already incorporated that in there, right? So I'm dividing by 9 over 56, which will give me that. So let's look at another example. Let's say I want to find the center of mass of a thin plate of constant density delta covering the given region. So in this case, the object will look like this, right? Here's the graph of y squared minus y, and here's the graph of y equals x. And again, we'll integrate in this direction, right? You could maybe integrate in this direction, but the problem with that is that you're going to have different boundaries here, right? Here the boundary changes to y equals x, so we're just going to do it that way. Okay. So first of all, we need to find the intersection points, right, where the curves intersect. So set the two curves equal to each other, right? So they intersect at 0 and 2. And then we'll also need to find the vertex of this parabola, but we can do that easily. And then look at a horizontal strip here, right? So again, where's the center of mass of the strip, right? Well, again, we're doing this in the y direction, so this distance will be y. And then to calculate the height of the strip, or the center of mass, right, take that distance plus that distance and divide by 2. Right, so and we have to do everything in terms of y because we're integrating in this direction. So that will be y squared minus y plus y all over 2, right? That's the center of mass. You can simplify that. So the center of mass of any given strip is y over 2 y, right? Now, what is the mass of the strip? Well, the mass of the strip, the length of the strip, will be given by this distance y minus y squared minus 2, right? And then multiply that times dy. That'll give you the area of the strip. And then the mass then will be given by, we don't know what the density is, so let's just multiply it by delta in that case. So the mass of a given strip is given by this, right? So, so again, we need to calculate m sub x, m sub y, and m. So the moment in the y-axis, again, is given by x tilde, right? This thing times the mass of the object, right? So we'll just take y squared over 2 times this thing. So the 2 just comes out front. Simplify, we'll get that, and then just integrate that, right? And then, so let's calculate this first, and then we'll integrate. So again, the m sub x, again, is given by this. So again, this would be done similarly. So go ahead and integrate that. You'll get that. So that'll be your m sub x, right? Will be 4 delta over 3. M sub y, again, we want to integrate this thing, right? So if you work that out, that'll give you 4 delta over 5. And then the mass, again, is given by just integrating the mass element, right? Which is that. So remember that x bar is m sub y over m. So taking our value for m sub y, which is this, dividing by m, which is this, right? That'll give you 3/5. And again, the y center of mass will be m sub x, which we calculated here, which is 4 delta over 3 divided by 4 delta over 3, which gives you 1, right? So the center of the mass then is 3 over 5, 1. And again, this has uniform density, so remember that think about where this would be, right? The center of mass would probably be somewhere, around here, right? There's more mass toward this end than there is here, which makes sense, right? This distance from here to here is, I guess, 2, right? So, let's see, I guess the distance there would actually be a little bit longer, right? So that distance is 2. That would actually be a little bit bigger. This would be like 3/5 in this direction, right? Which should be somewhere here. And then it would be up at 1, right? And again, it should be interior to your object. Okay. Let's look at another example. Let's say you want to find the center of mass of a thin plate of constant density delta covering the given region. And so the bottom curve here is given by 2x squared minus 4x. The top curve is given by this. Again, you don't really want to integrate this way because the curve changes from here to here. So try to integrate so that you can always have the same curve on the top and the bottom, right? If I integrate this way, I've always got this curve on top and that curve on the bottom. So again, just sort of setting this up, right? Where is the center of mass of this strip, right? Well, take the average, right? You take this height plus that height, and then take the average there, right? So that would be given by that. Simplify that, that'll give you the height of the strip. So, or the center of mass of the strip. The length of the strip will be that distance plus that distance, right? Or in this particular case, because the curve, the y coordinates here are negative down here, right? Which should actually be that distance minus that distance, which will be given by that. And the area element, again, will be the area of the strip here, right, which is given by that. And then the mass, again, we don't know what the density is, but we know it's uniform because it says so in the problem, will be delta times dA, right? So, so the moment in this case, again, will be our element of mass, and then we want to multiply that times the distance that this is from our lever arm, right? Now, in this particular case, right, we're looking at, if we're looking at delta y, we're looking at this distance here. Well, we calculated that already. That's given by this. So just multiply that times that, which will give you that. right? And then just integrate that from wherever this is to wherever that is. Again, it looks like it's going from 0 to 2. You could figure out where those are, but that looks about right. You might want to verify that just to be sure on an exam. Then just integrate that, and that will give you m sub x. So if you integrate that, you'll get negative delta over 5. And then the mass of the object, again, is given by that, taking the mass element and integrating. So that'll give you negative 2/5 for y bar, right? And then in this particular case, we won't bother calculating x bar, but if you do work it out, it does give you 1. Let's look at another example here. Let's say you want to find the center of mass of a thin plate. So we'll assume that the plate, is doesn't have any thickness to it, right? Covering a region bounded by y is equal to x squared, and the line y equals x. In this case, the density will vary linearly, right? It'll be 12x. And so if you look at the shape in this case, the shape of the object will be given by this. Again, the object gets more dense as you go further out in the x direction, right? So it won't be it'll almost have 0 density here, and then as you get out here, it'll have a density of 12 times your x distance, right? So in this case, mx will be given by this. Again, let's make our rectangles go in this direction. In this case, you could make them go in this direction too if you'd rather, but let's just make the rectangles go in this direction. So the distance to the center of mass here would be this height plus that height divided by 2. And the height of this strip will be this height x sub 1 minus x squared, right? So that's the height of the strip, that's the density, that's the distance of the point from our axis of rotation, right, which is given by this. And we're multiplying it times the density, right? So go ahead and work all that out, and that will give you about 1/2, right? Doing a similar thing for m sub y. Now the x-axis in this case will be relatively easy. This distance is just x, so we're going to take our mass element, which is the length of the object times the thickness times the density, and multiply it by x, right? Work that out, that'll give you 3/5. And then we need to calculate the mass of the whole thing, right? Which would just be our mass element here, which would be the height times the density times the thickness. So go ahead and work that out. That'll give you 3/5. And then just divide, right? Divide this by 3/5, right? Divide 1/2 by 3/5, and then divide 3/5 by 3/5. Or sorry, by 1. I'm sorry, the mass element is 1. Divide everything by 1, right? You'll get 3/5 and 1/2 for the center of mass, right? Which kind of makes sense, right? I mean, hard to tell exactly where this point is, but it looks like, 3/5 would be more than 1, so that'd be somewhere probably, I think this is probably, let's see, where's x squared equal to x? So that would be 1 there, yeah, so this would be more than halfway there, and about half the distance from there to there, which would be 1. Okay. Now, one thing you can do is, if you don't like setting up those problems the way we've already done them, you can just use these two formulas if you've got the density between plates. So, I mean, just to show you, we could have done the previous example just by plugging into the formulas rather than just sort of thinking about it. So this is kind of a mindless way of doing it. I don't know what's better, but that's the one reason why I didn't show you these formulas earlier, is to kind of get you to think about where the parts of the thing are working. But you can just plug these into the various formulas, and you can see that we get the same answer without having to really think about it geometrically, right? You get the same value for the center of mass. Just plug in one curve and then the other curve. I guess you just have to keep in mind, when one curve is always above the other one, and that will give you the answer. So there is kind of a shortcut for doing those if you want. let's maybe go back and do this example using formulas. These sort of shortcut formulas. If you remember, if I can find the original slide here. Was this one? Yeah, I think it was this one, right? This is what we got for the center of mass. You should see that we kind of had to think about it, think about the axis of rotation and stuff like that. Again, if you just plug into the formula, it will kind of just spit out the answer, right? So plugging into the top formula here, I just do the square root of x minus x over 2. You know, put in delta and the density and then x, right? I get the same answer that I got before, right? Without really having to think about it, just plugging into the formula. Same thing here, I just plug square root of x in for the top function, x over 2 for the bottom function, and then just work that out, and we do get the same answer that we got before. I think, right, 252 over 405. So the formulas are a little bit more expedient. So if you're going to take a class like a mechanics class where you have to calculate these, they might just give you these formulas. I don't know, but it's nice to know kind of where they come from. So whether you want to think about it or just use the formulas, right, you can do it either way. You should get the same answer. So let's look at another thing here. Let's look at centroids, which are centers of mass without regard to density. But basically we can just set the density equal to 1 in these problems. So these would be things where you don't necessarily have plates, so you might find that the center of mass may not actually be on the object itself. But let's say that you want to find the center of mass, or in other words, the centroid of a thin wire of constant density delta shaped like a semicircle of radius a. Right, so we've got something sort of shaped like this, and we want to figure out, again, where would you balance this? Where would you put your finger to balance this? Now, so again, you're kind of looking down top on the wire, so gravity is acting in the direction into the paper. So if you think about it, it should be centered here in the center, but it's probably not going to be on the wire itself. So maybe you'd have to have like an armature or something that would, very light armature that would come from the wire to this point, so you could sort of balance it like that. So in this particular case, you might see that the center of mass is not actually on the object itself. And it might be easier in this case to just switch coordinate systems. Rather than dealing with x and y, it might be easier to switch to polar coordinates. It's pretty obvious in this case that the center of mass in the x direction here will be 0. So let's assume that this is the x and y axis here, and that this is the origin. It's pretty clear that that's going to be 0. We can calculate it out. But let's just calculate y bar, the center of mass in the y direction, right? That's going to be this, right, divided by the mass of the wire, right? And the wire is just circles or semicircles, so you wouldn't really have to use calculus to calculate that, right? It's of radius a, so the density is just going to be the length of the wire times the density. So we've got, we've got half a circle, so the length here would just be a times pi. Multiply that times the density there, and that should just give you pi on the bottom. Now for the top, if you integrate that, again, you have to kind of think about, well, how much is the mass element and where is it, right? Again, if you're thinking about this in a radial form, you've got this little change in angle. What is the mass of that little piece there, right? So that'll be the arc length times the density, right, which will be given by that. And so just go ahead and work that out, right, that it should give you 2a over pi. And so again, you'll notice at this point 2a over pi is not on the curve, right? 2a would be twice the radius, that'd be somewhere out here. Then you divide by 3 is going to put it somewhere down here, right? For the center of mass in that direction. Let's say you want to find the moment about the x-axis of a wire of constant density that lies along this curve, say from 0 to 1, the curve y is equal to x cubed. So in this particular case, right, you've got the curve here, right? Let's integrate in the y direction. So if you look at the arc length here, right, the length of the curve is given by that, and then you would just multiply times the center of mass, which would be given by this. So this will be your curve here, right, and you're integrating this from 0 to 1, or sorry, I guess we're going the x direction here, right, from 0 to 1. So think about, what is the distance that this particular point is, say, from that point or sorry, I guess we're calculating m sub x, right, which would be this distance, right, which would be x cubed, and then just integrate that, right, that'll give you that, and then calculate the mass in this case, which would basically be the arc length, right, times the density, and then just go ahead and divide those, and that should give you the answer for that. Now, as far as fluid force and weight density, right? Again, we have the fluid force again is equal to the product of the distance h from the plate centroid and the weight density W in the area. So let's say that you have a flat isosceles triangular plate with a base of 6 feet and a height of 3 feet is submerged vertically, base up with its vertex at the origin, so that the base is 2 feet below the water. Find the force exerted by the water against y to the side of the plate, right? And so I think we did this example back in 6.5, but we might have thought about this a little bit differently. In this case, you can just take 0.5 times, so I'm basically calculating the area of the triangle, which is 1/2 the base times the height, which will be A, which is 9, and then I will take the weight density, which is 62.4, times the height, which is 3, and then 9, right? And you should see that that will give you the same answer, but it's a lot easier way to do this than maybe doing it the way we did back in the last section when we had to integrate. There's some other stuff in this section. I think we'll just skip that, though. I guess maybe one last theorem I should mention is that in a plane if a plane region is revolved once upon a line in the plane that does not cut through the region's interior, then the volume of the solid it generates is equal to the region's area times the distance traveled by the region's centroid during the revolution. So you could kind of use this to maybe simplify. You could use this formula to maybe calculate some of the volumes of revolution we did earlier. So if you wanted to calculate sort of this volume of revolution rather than doing an integral, you could basically just plug into that formula, assuming that you can find the centroid, which might involve some calculus. But all right, there's a little bit more to this section, but I think that pretty much wraps this up. So if you guys have questions or anything, I know this can be kind of a long, involved section, so if you have questions, just let me know.